Do I have to hold down on it? I know.
I don't think so.
Hello.
Hello.
Hello. Can you hold it? Yeah, I can do it. Okay.
If it
You can
doesn't-
put it in presenter view.
Oh, how do you do that? Like in case you haven't already, please scan the QR code so we know that you came to this meeting.
I think we're doing. I think we're fine. I think but no, that's gonna early sound. I think the stronger one anyway. But it works. It works. Yeah. Oh, sorry.
Hey, hi everyone. Thank you for coming. Today we're going to be talking about avionics and recovery, and I am here with the sub-team leads of avionics and recovery.
Yeah, my name's Lisa. I'm the avionics spaceport lead. So if you guys want, today we are having our meeting at 6:30 p.m. in MAC. So if you guys, maybe you guys want to come today, that would be awesome. Hi, I'm Liz. I'm the spaceport recovery lead. Our meeting's on Thursday, so yeah, if you want to come, you definitely should.
Yeah, and for those just coming in, just make sure to scan the QR code, just so you know that we know that you attended the meeting. So yeah, this is just the schedule for the next GMs. The next one will be tomorrow at the same time, I believe, but the room location will be announced in the Slack. Yeah, today's avionics and recovery, and then the next Monday and Tuesday we'll have structures and testing, respectively. Yeah, so today we're going to be talking about what avionics and recovery is, the types of recovery systems that we have, separation, because there's different types of separation, recovery materials, so everything that involves recovering your rocket after it lands. The avionics bay, we're going to be talking about carbon CO2 ejection, flight computers, and then we're going to be talking about how to use Altium. So if you guys haven't downloaded that already, please try to so you can follow along.
Who joined the like LCM, like figure all the cloud stuff. So I think
That I'm not sure like at the moment, but we could use manufacturer part search, so we won't use like the UF libraries. I'm sure I can like probably like explain more if you want like on Slack. Afterwards.
Yeah. So what is it? So yeah, basically after we launch every rocket, we don't want it to be the last time we launch it. We want to be able to reuse some of the parts, such as the airframe. So our avionics and recovery basically makes it so that it has a soft landing and we can reuse those parts. So yeah, parachutes slow the descent of an object. And then avionics is everything that involves like the sensors and the altimeters that trigger that deployment of the parachute. So for example, if you want the parachute to deploy at apogee, your avionics would kind of help you with that programming when it will deploy.
So we're gonna be talking about the recovery systems. So there are two types. There are two, no? Hello?
Oh,
Try this one. There are two types. We have single deploy and dual deploy. Single, as it kind of sounds, is just one parachute, whereas dual deploy is two. For simple, it's mainly for smaller rockets. There's lots of drift because you only have one, so it can kind of go kind of far. Those are for like the L1s, which are not very big. And then we have dual deploy, which, like I said, has two parachutes, and it reduces the drift because one of them is a lot bigger than the other. But where was I going with this? It reduces the flight time, so it doesn't have as much, like, it doesn't have as far to go. We use those for do you use them for L2s?
Yeah,
We use them for the L2s as well as our competition rockets. So this, as you can see, is single deploy. We have one parachute come out at apogee and it just floats down pretty much. And then we have dual deploy here, where once it reaches apogee, the drogue parachute, which is the smaller one, comes out, and then it descends to a certain altitude where main comes out, and that'll lower it down to the ground from there.
when you only have one parachute, it usually takes a lot longer to find your rocket. Well, if you have a small one, it kind of like speeds up the process to when you need the big one to deploy. So it kind of speeds things up.
So technically, like at apogee, we have the drogue parachute come out, which is like a small parachute that's just like to slowly slow down the rocket. And then that's just aiming to like slow down the rocket till it gets to like a certain pre-programmed lower altitude. And at that lower altitude, the big parachute comes out. So that's the main parachute. And that's the one responsible for mainly slowing down the rocket so that it reaches the ground safely.
So we can control where our separations occur. We used shear pins and rivets. You attach them to the airframe, and shear pins you put those on the sections that are going to separate because they'll break very easily, whereas the rivets won't. So those will be in places where you don't want it to separate. So we have our materials. We have obviously the parachutes. We have D-links, eye bolts, parachute protectors, recovery harnesses, and swivels. And you combine them all pretty much, and that'll keep the parachute where it's supposed to be without ripping it off the rocket, because that would be very bad. And then it would fall out of the sky. We don't want that. So this is a diagram of where we put them exactly. So as you can see, the main parachute is in between the nose cone and the avionics bay, whereas the drogue is in between the rest of the airframe and the avionics bay, and we connect them with the harnesses. And parachute protectors are very important. We don't want the parachutes to get damaged. And you connect them in this kind of format. Yeah.
The protectors are so it doesn't catch fire when the ejection happens.
Because we use black powder, and that can burn your parachutes, and we don't want that. So our methods of ejection, we typically use black powder, but like we just said, that can possibly damage your parachutes or even the electronics because they're so close to the avionics bay. It works almost every time. It's reliable, but we also use CO2 ejection, which is the opposite of black powder. It's cold gas. It won't hurt your electronics, and technically it works better at higher altitudes. Um, and right down here we have a picture of our CO2 canister mount and how we just the system's design. The CO2 canister is the far left, and then this is the mount, and then the pin that will be pushed in, and it will what's it called? Puncture, thank you. Puncture the CO2 canister, which will escape through the holes in the side of the canister. How we do that is with a black powder charge. So it's a combination of both. You put a tiny little bit of black powder right in here, and when you seal it and light it, it pushes the pin on the spring into the canister, and then the canister will bounce back, or the spring will bounce back, which will release the gas.
Yeah, so I'm gonna give a brief overview of the avionics system, which is kind of like the brains, and it tells the rest. It kind of controls when the recovery events happen. And this is, as you could see, that's the avionics bay, and that's its location within the rocket. It's a critical component that's housed within the avionics coupler, and it has various electronics that are mounted on a sled within it, such as altimeters, batteries, and arming switches. Altimeters function by measuring they measure air pressure, and we can correlate air pressure to the altitude. So based on the altitude that we are at, we can determine what critical events need to happen, such as when the parachutes need to get released and like drogue and main ejection. So they measure the rocket's altitude, and they send signals to trigger the ejection charges at apogee and at also the pre-programmed lower altitude. And those function to deploy the parachutes. The altimeters are typically powered through 9-volt batteries, and we use arming switches to safely activate and deactivate the altimeters, and we typically do that when we're on the launch pad. We'll also discuss the importance of redundancy. We usually use 2 altimeters in order to, in case one fails, we have a secondary altimeter to also trigger the ejection charges to send the current to do the ejection. And it's also strategically positioned such that it can separate the rocket into the 2 sections. So here's another rendering of the avionics bay. As you can see, it's kind of in the cylindrical shape, and you can see over there, there's like the arming switch on the side, which we can insert and then kind of arm the altimeters. That's to actually power them on, and we do that on the pad. You can see the 2 altimeters over there. And these altimeters, as said before, they house some sensors such as a barometer to measure air pressure and an accelerometer to measure acceleration to determine when the critical events happen. So yeah, this is again the altimeter, one of the altimeters that we use, which is a stride logger. This is a commercial off-the-shelf altimeter. We're actually working on developing our own flight computer this year, just creating the PCB for it and kind of mounting all the sensors on it, and kind of using that as a redundant altimeter for our rocket this year. As I said, they work by measuring air pressure and calculating altitude changes, and we can pre-program the altimeter with the lower altitude at which we want the main to come out at. And this can help in minimizing the damage done to the rocket by making the parachutes deploy the correct time to safely slow down the rocket to a descent velocity where it won't actually hit the ground really hard. And it also has it collects data, so we can have that data for post-flight analysis. So this is the open rocket simulations that we do to determine at what lower altitude we should deploy the main parachute. We use the open rocket simulations to optimize the recovery configuration that we do. And this software kind of, as you can see, it helps model the flight of the rocket and predict the behavior under various conditions. As you can see, there's a graph of vertical motion over time. And this is critical to ensure that the parachute parameters are correctly chosen, such as like diameter and mass are correctly input into the simulation. Um, and that's going to affect like various things like flight time, apogee, and descent velocity. And we can also like simulate wind speeds in here and to understand how the rocket's recovery will be affected by that. So here's also some basic flight computer theory. The flight computer is responsible for controlling the ejection process based on the data that is received from the sensors, and it detects stages in the flight, such as the apogee and the target altitude at which we're going to deploy the main parachute. Um, the computer only has, there are some drawbacks, such as noise and sensors, and the computer only having a limited amount of data to work with, since it collects data only every 0.5 seconds, which introduces challenges such as the acceleration limits and then also the sensor noise. And this is just some more tips on ways we can optimize rocket recovery. Wind speed is plays an important role in drift radius, and it should be factored into simulations and kind of planning in our recovery layout. The length of the recovery harness should be adjusted to match the rocket size, and it should be at least 2 to 3 times the length of the rocket. And it's important to check the motor type to ensure that it includes the necessary ejection charge. And parachutes also need enough time to deploy. So we need to set the main parachute deployment to be at least 500 feet above the ground to avoid hitting the ground too hard with like too high of a descent velocity. Um, and then, so I have a little Altium demo that we can do. We don't know how to connect things to my cable.
Should be my cable expert, by any chance?
Did the HDMI plug directly from the screen?
Yeah, it's in that, on that
You
screen.
can use this and then control it here. Control the output from that screen, but
It wasn't working, right? When you plugged in that one.
there should be an option in that little screen over there for what's going to put that there. And you can switch.
Oh, technology. Man. Wow, very cool.
People learn to read. So yeah, this is gonna go over a little bit of an Ultium tutorial. So, do you guys have Ultium like downloaded? Okay, cool. So this is when you open up Ultium, you shouldn't have all these projects, but you could go to project, or you could go to file, new, and then press project. And this would create a new project. So we're just gonna put like sample or something like that. And then this should all be empty. And you can press create. And this would, as you can see here, it creates a new project, but it says it's this little folder, and then it says no documents added underneath it. What we're gonna do is we're gonna right click and we're gonna press add new to project. And we can add a schematic to the project. And then we can right click and we can add new to project, and then we can press PCB. So what the schematic is have any of you guys like worked with breadboards before by any chance? So yeah, so it kind of just like, it's kind of like that, except the PCB or printed circuit board, it just has all the connections like within instead of outside, like externally through wires. Like the electrical connections are just internal to the board. So they're just copper traces within the board. And in industry, these are sometimes called circuit card assemblies or PCBs, printed card assemblies. So it's kind of like a breadboard, but it's better because the wires like don't get ripped out during flight, or there's no like possibility of it just like disconnecting. So everything's internal. It's a lot more kind of protected. So the schematic is where we actually put the physical connections. Well, not the physical connections, but what we want to be connected to what. And then this layout is where we actually draw out the physical connections and where everything will go on the board and how it will look. So today we can do a simple connection, a simple project. So we are just gonna like connect, we're gonna get an Arduino, which is a microcontroller. So we can search up Arduino, and we can press this. Actually, search up Arduino, press enter. We can get the second one. So the way you can tell if a component, we're currently on manufacturer part search. So if you don't have manufacturer part search, or you don't know where manufacturer part search is, you can go to panels, and here you have all these different tabs. So you could go to components, which is where, as the question was asked earlier, you can get a bunch of libraries that are from UF and have a ton of components. Or you could also go to manufacturer part search, which has components already like available from various like manufacturers. You can search up different kinds of things. So we can put this Arduino, which is a microcontroller, on here. And let's say we want to connect an LED to this Arduino, and we want to power it and use PWM to drive their Arduino.
So we can also search up LED. We can use this LED. And something else I wanted to touch upon is that as you can see, there's like these little components. When it's green, that means that component's available and you can use it. You can like drag, and it has a footprint that you can drag and put on the schematic. If there's no footprint, then it's not going to be green. But that means we can use it and it has a footprint. So we have this LED and we want to connect it to the Arduino. This kind of specifier is kind of which component. So let's say we have multiple LEDs, multiple diodes, we can specify this to D1. If we have like 2 or 3, it could be D1, D2, D3. Those are just the names. And in order to limit the current to like a current that's won't fry the LED or won't like harm the LED or the Arduino, we're going to put a resistor. So we can go here. We can search up. If you're doing like a more complicated design and or you're doing something else and you want to like actually like make something, you would probably need to pull up the data sheets of various components and look to make sure like the current and voltages are suitable and they match like the requirements of your design and the scope of your design, and to make sure that there won't be like an overcurrent or none of the components would get damaged. So we can get a resistor and we can put this one to 220 ohms. That's like a common resistor value that's typically used with LEDs. And then we can connect that using, if you go up here, it says place wire. So you can press place wire and we can go to the end. When you see the red X appear, that means that that is actually like making a connection. So you press from here to here, and that creates a connection between the resistor and the LED. And then we can also place a ground connection. So we can place a ground power port. We can go up here to the top. We can press this and place this over here. And then we can connect this to one of these pins, one of these digital pins. So the way we connect this, and also we would need to write that this is R1. If in case we're using multiple resistors, we can have R1, R2, R3. We're going to label this R1 so that we know that this is resistor 1. Yeah. And then if we want to connect this, we could either do it 2 ways. We could do it directly, so we could connect it like this, or we can draw out a line, and on here we could write, let's say, we can right click it and we can press place, and we can press place net label, and here we can write, let's call it light. And we can also do the same thing on this end. And I can right click and I can press net label, and I can write light. So as you can see, the red squiggly line goes away. So that means that that's a proper connection that's formed. It's because you can just write the name on 2 ends and that would connect it to electrically. And then we might also want to do a connector to give power. to the Arduino. So we could do header. We can look up header pins to provide. So we could use, let's say we want to use this one, do it here. And to rotate it, we can also press space. We can write P1, label it, and then we can extend this. And let's say we want to add 5 volts. We can right click on this place ground power port, and we can now change it to place 5 power port. We can also put it here since this is where the Arduino is powered. And then we can connect the other end to ground. Is everyone following along so far? Or does anyone have any questions?
How do you change the ohms point of the resistor?
So practically this, you can right click it. Right click or click on the resistor. And then you can kind of click on the value here. So you right click or you can click on the resistor. Yeah. You just kind of click on it and then the properties tab shows up. So I changed the comment. So what the schematic does is that it kind of creates just the electrical connection. When you're importing the components, you just have to make sure that the footprint matches the resistor that you want to use. So like, let's say you have like a 1 ohm resistor and a 220 ohm resistor. As long as like the footprint matches the actual resistor that you want to use, that's all that matters. And the footprint is kind of like the sizing. So like the connection will be established no matter like what resistance value you're putting in. But there's different sizes of resistors. So you just want to make sure the resistor, so you can read here the description, but you want to make sure that the sizing matches the resistor that you're going to use. So even if you want to use a 220 ohm resistor, but you can only find like a 1 ohm resistor, but it has the same footprint, like the 1 ohm resistor and the 220 ohm resistor have the same footprint. You can use it and then just like swap it for a 220 ohm resistor when you order resistors. Yeah, I kind of, for this one, I kind of just searched header and yeah, it should be the first one. But yeah, when you're making a design, you can honestly choose whichever ones work best for your design. So, depending on what connectors you need, you could search it up, read like data sheets on the components that you're using and see which one better fits your design. Does anyone have any other questions, or is anyone else confused or stuck? Okay. So this is, for example, this is like kind of a simple circuit you can do. And then we can, if we wanna, we can go and save it, and we can label, we can call it something like, let's call it. And then we can go to the PCB document that we created. And then we can, in order to import these components from the schematic, we can go to design, and then we can go to import changes. Give me 1 second. So you can go here, you can go to design, you can go to import changes. And we have all these components, and we want to validate if, when you press validate, that just validates that the changes are valid, that the connections make sense. So you can press validate, and it shows you, yep, the connections make sense. And then we press execute, the changes are actually executed. Sometimes when you press validate, the changes, like it says that they're not valid. Sometimes you can press execute and they'll still execute. So that's sometimes a bug. Then we can drag these components onto here, onto the board. And when it lights up green, that means it's not happy. So it's just something is touching where it's not supposed to be touching.
And this is kind of the physical location on the board. We want to get the lines between the components like as close as possible, so there's as little noise as possible, like in the connections. We drag it like that. And then when you press 3, that kind of shows you the 3D view. So this is what it would look like. It would just have the connections for these components. You would have to orbit components separately to mount them on top, and kind of solder them in. So yeah, and then you can press the space bar to rotate them to make it look how you want. And then we can go to the top layer. We can go to route. You can do auto route, which is, some would say you could individually route all the connections, or you could do something called auto routing, which it does route all the connections. That's kind of problematic if you have a large design. It sometimes does not route all the connections. Since we do have a really small design, we can just press auto route all, and it does route all the connections. Afterwards, what you could do to make sure all the connections are valid, you could press Control A, and that just makes sure that all the connections are completed. That's called auto routing. If you're working with a really, really large project, I would suggest like doing all the routes yourself, because sometimes auto route can mess up the routes. Oh. Did anyone have a question? Yeah. The what? Oh, okay. Yeah, so you can go, when you go to the schematic, you can, so you see where the ground is right there, where it says place ground power port on the top. Yeah, you right click that, and it has a lot of different options. Like if you want to just place a different power, you could just press place VCC port, and then you can change VCC to whatever voltage you want. So this is our PCB board for now. And then if we want to change, oh.
How did you?
So what I did was I went to design, and then I went to import changes. You might need to save the entire project before doing that. You might need to save to server, or you might need to save the actual project before doing that. Did it work? So I think on the actual project, you can right click and you can press save, and that should just save it. Were you good? Yeah. Okay. So then we can, if we want to like change the size of the, like let's say we want to make this smaller, we don't want this to be like this big, because we don't really need that size of a board. So what we can do is we can go to, I changed to the keep out layer. So we can you can go all the way right, and you can select keep out layer, and then you can press place, and then you can go to keep out, and you can put track. So then you can draw kind of the shape that you want your PCB to be in, like what you want your physical
PCB to be in. So let's say I want it to be a lot smaller. So let's say I want it to be this big. I can draw whatever shape I want. I can draw whatever shape I want around the PCB or around the components. And this will create this. It'll be a weirdly shaped PCB. It's okay. Yeah, yeah. You can make your PCBs weirdly shaped if you want. There's no rule against making your PCB weirdly shaped. And then, yeah. So you can click you can go to design, or wait, place. You can first select one of the traces that you made and then press tab. You can press tab and that selects all of them. And then you can put polygon 4. Oh wait, no, actually not polygon 4. 1 second. Oh, then go to tools and then oh, design, and then you can go to board shape and you can press define board from selected objects. You can design and then board shape, define board from selected objects, and now it becomes smaller. So, and now your PCB looks like that instead of like the entire big PCB. And then there's other things you can do, such as place a polygon 4. So place polygon 4. So what a polygon 4, it kind of creates like a strong layer, like a strong like top layer and a strong bottom layer. You kind of want a strong ground layer so that it's like the grounding is like equal over the board and that all the components are like well grounded. You can also create a strong like top charge layer. So that's like, let's say a lot of your components are using 5 volts. You might want to create a strong top layer that is 5 volts across the entire board. And how you would do that is you would go here and then you would go to polygon 4 and then you would kind of draw out the shape of the board. So, and then you would go to properties. And so this is on the top layer. So because we're currently in the top layer on the bottom, so we want to create a strong like 5 volt top layer. And there's various you could do a solid plane, you could do a hatched, you could do none. We're gonna do hatched. That's it.
So that created a top plane. So as you can see, this like hatched. You could do the same thing for the bottom. So you could also do the same thing. You can go to polygon pour, place, uh, place, polygon pour, do the same process and do it for a ground layer. So let's say we want the entire board, the entire board to have a strong ground plane. So we can go to properties, and then we can go to changing to bottom layer, and we want this to have a ground net, and we want it to be, let's say we want this to be hatched, depending on how much copper we want and like what our design considerations are, we could either make like a hatched or a solid ground plane. And this helps just to make sure that everything is grounded, like all the ground connections are stable, and to prevent like any instability in our design. So then we press enter. Are you guys following along so far? Okay.
A lot, I still on my making the.
Oh, okay. Okay. So the way you do the smaller PCB is that um you go to keep out layer to this one on the far right. And then you should be able to kind of trace out the design that you want. Or you go to keep out layer and then you go to design, and or after you have like drawn out, so you need to draw out like the little board with the keep out layer. So when you go to keep out layer, you can draw out like the little pink box around your design. Yeah. So you go to, so for example, like, let me go to, and show before them. But yeah, you go to the keep out layer, and then you just draw the little pink box. Like when you press and you're in the keep out layer, you can see like it forms like the little the pink box, right? Yeah, and then you just make a trace. So you just kind of draw the pink box around your design. Yeah, so you go to, and this is this is like, these are some of the last steps that you do. You do all you make all the ground plane and the top plane, and then afterwards you can go to place, and then you can press place polygon for, or well, actually, yeah, and then that should be kind of the end of the these are some of the last steps that you take in the creating of the PCB. So yeah, are you still needing help with the? Okay. Does anyone else have any questions? I can also help you afterwards. Does anyone else have any questions on the making of the PCB?
well, if nobody else has any questions, I think that's kind of the end of the tutorial, but and if anyone else has any other questions, like you can always reach out on Slack. There's a really good series of videos that you have made that kind of go step by step on Altium and give like a really, really good Altium tutorial that I can also like send if anyone wants access to that. Yes, yes.
We'll be uploading it to YouTube,
Okay, to YouTube.
so you could just look up UF Swamp Launch Team.
Yeah,
If not, it will be in
and if anyone else wants the videos, feel free to message me. It's really good, comprehensive.
That's the thing, for which one? Tonight.
Tonight at 7:30. Yeah.
Okay.
So we're doing that tonight, and then your recovery meetings are on
Thursdays
Thursdays
at 7:30.
at 7:30, and mine are on Mondays at 7:30.
Mhm.
Does anyone else have any questions? And if not, that's the end of the tutorial. So thank you so much, guys, for coming.
Yeah, so this flight dynamic, oh. Okay, cool.
There you go.
So yeah, pull up tomorrow to Flight Dynamics at 4:30 McCarty 8, the same room. And then we'll be doing a RAS Aero demo, which is another type of simulation software. It's pretty easy to download, pretty straightforward. Oh, and also, if you did follow along the Altium tutorial, make sure to DM Reed McAdam on Slack. He made the GEM announcement for today, and then just DM him your file. But yeah, did anybody not scan the QR code for attendance? Okay. And yeah, certs applications are out if you want to look in the Slack for that. They're there. There's just like a Google form. Yeah, have a good day, guys. Hopefully we see you at the sub team meetings. I hope the recording caught it then.